Morning, everyone. So yesterday we started into our solubility equilibrium chapter. We started looking at saturated solutions. Basically, we're going to dissolve solids into liquids. There's a certain sort of maximum amount that manages to dissolve. We refer to that number as solubility. We saw that we could make saturated solutions in two different ways. One was by dissolving a solid where it follows the mole ratio. Towards the end, we ended up doing mixing of two solutions together because those are two completely independent solutions. They actually are not going to follow the mole ratio. So I'm just going to give you a quick warm-up question here for you to just practice. So in this case here, I want you to write equations showing the equilibrium in a saturated solution of, let's do PbBr2. Let's say that's part A of the problem. Part B of the problem, if 0.844 grams can dissolve into 100 milliliters, I want you to calculate the molar solubility. So calculate the amount that dissolves in moles per liter. And then C, I want you to find the concentration of lead ions and the concentration of bromide ions in solution. All right, so I'd encourage you just to pause the video, give that a try for yourself. All right, so assuming you've done that here, a couple key things here. First thing to identify in this chapter here is what is potentially the solid that forms. In this case here, there is only one solid, so they're looking at this lead-2 bromide compound. When they actually say saturated, right, saturated, pictorially here, it's I've dissolved in so much that my solid is just left over. Saturated actually implies equilibrium, right? What's in equilibrium here is the PbBr2 is actually breaking up, it's dissolving. We always put the solid on the left side, so PbBr2 as a solid. When it dissolves, what are the ions that it breaks up into? So we're just going to get some lead-2 ions. We're going to get 2 bromide ions for the dissolving. That's only the one direction here, so rate of dissolving. Because we are in equilibrium, we need to have the reverse reaction. The reverse reaction is, yeah, we've dissolved so much maximum, and now it looks like macroscopically the precipitate is there. That's because as things continue to dissolve, the particles in solution are continuing to solidify back out. We call that reaction there the rate of recrystallizing, becoming that lattice again. And because we're in equilibrium, we know that these two here are actually equal. So that's part A here. That is the equilibrium that's established. We have solid on the left side, and we have our aqueous ions. Now, reading part B here, if it says, if 0.844 grams can dissolve into 100 milliliters, this actually implies that is a maximum amount, right? Because if I try to dissolve 0.85 grams, well, it's not going to dissolve anymore. I've already hit that saturation limit. Any extra solid is just going to sit around extra. So they're describing to you here, this is the solubility. Currently, unfortunately, the solubility, perfectly fine for you to express, well, I can dissolve 0.844 grams. It's in 100 milliliters. I'm just going to convert that to 0.1 liters. Well, that's going to be 0.0. 0.844 divided by 0.1 gives you 8.44 grams per liter. That already is a solubility. But what they want is they want to introduce here, can you calculate molar solubility? Can you re-express this limit that can dissolve, but can you re-express it in concentration, in moles per liter? We did a couple of these yesterday here. To find the molar solubility, all we need is going to our periodic table. If I know the solubility currently is 8.44 grams for a given liter, remember I didn't actually dissolve 8.44 grams. There was 0.844 in 100 milliliters. In a liter, though, you can dissolve 8.44. We need the molar mass in the periodic table, get rid of grams, and get to moles. Then potentially, if we need to follow mole ratio, I can use this molar solubility. So lead is 207.2 plus 2 times bromide, 79.9, gives you 367. We still want to do 1 decimal place for the molar mass. So 8.44 divided by 367. The molar solubility, that same number, just written in different units here, is actually going to be 0.0230 molar. So again, you can think of that here, the concentration. So this number here is the concentration in solution when you hit saturation, or you can think of this as you manage to dissolve 0.0230 moles of solid per 1 liter. Right? So that's how that number is specified here. Again, that's why for solubility, they sometimes say, oh, solubility is just a concentration when you're at saturation. It's because when you manage to dissolve this amount of solid, that is identical to the solution. Let's find the concentration then. Well, in this case here, I'm starting off with solid, so let's follow the mole ratio. If I have PbBr2, let me just rehash this for you here. PbBr2, it's in equilibrium. If I can dissolve 0.0230 molar, that's how much, let me emphasize here, that's how much dissolves. This is going to break up to form a 1-to-1 ratio. So I'm going to get 0.0230 of the lead, and 1-to-2 ratio with the bromide, 0.0, give or take a little bit of rounding here, 0.0460 molar. All right. And it's implied the part that actually dissolves is now gone. That doesn't mean that the solid is completely disappeared. That only tells you by the time we hit saturation, a precipitate just forms. We wait long enough for an equilibrium to be established. There is still solid sitting there, but how much has actually managed to dissolve is actually only this 0.0230. I still do have solid present. I have to have solid present so that I have both reactions still occurring. Right? So what I pulled up for you here, this is actually the solubility chart here. We already saw this back in grade 11, but we'll use it a lot in this chapter in grade 12. Again, I introduced this to you last day. Basically, every compound is soluble to a certain degree. We just set our arbitrary limit here. If I manage to dissolve more than 0.1 molar at 25 degrees, I'm going to call you soluble. So any of these ones here on the table that say soluble are actually going to dissolve greater than 0.1 molar. In this case here, anything that are low soluble is anything less than it. In general, this table is set up with combinations. The most soluble are up here. The least soluble are actually down here. And if you remember from this chart here, how do you read this? Basically, we're going to start off testing compound by compound. You start off looking, this is mainly for ionic compounds. You look up the anion, which is negative, and then what you do is you mix and match it with the positive. By doing the crisscross of that combination here, we're going to see on the side, is it soluble? Soluble means it dissolves very well, dissolving very well. So soluble means it dissolves. So we're going to put aqueous. Whereas if it says low soluble, it means it dissolves poorly. And in this case here, dissolving poorly, we're going to say solid. Let me just hit one nice simplification here. You always have your table, so you never need to memorize this. But it's good to note some things that are always going to be soluble. And you notice starting from the ones that are really, really soluble up at the top here, in fact, any negative ions with any of these positives, they're classified as soluble. So what's so special about these positives here? Well, we're looking at any alkali salts. We're looking at hydrogen salts. We're looking at ammonium salts. All of them are +1 salts. That's one good way of memorizing it. So in that case there, you can actually conclude, sort of memory hint number 1, all alkali salts, all H+ salts, all NH4+ salts are always soluble. They're going to take a lot before you actually hit saturation. So if, later on we're going to see this, if I need to have any negative ions in solution, if I need phosphate in solution, I'm never going to have a pure bottle of just pure phosphate. But all I want is I want to have a salt that contains the phosphate ion. I know water is going to dissociate the positive from the negative. Maybe I match that phosphate with some counterbalancing alkali ion, lithium phosphate, sodium phosphate, because it guarantees me every alkali ion is completely soluble, it completely breaks apart. So this is really useful for putting negative ions in solution. Another nice memory aid for you here is, what about going the other way? What if I wanted to put some positive ion solution and I wanted to reach for a bottle, I want to guarantee that it's soluble. In fact, we learn in this situation, nitrates with any positives are also soluble. So that's another hint that I would take here. All nitrates, all solids that contain the nitrate ion NO3- are soluble. So let's say I needed tungsten in solution. Well, I'm not going to have a bottle of just pure tungsten positive. What I will reach for is maybe I'll take a compound tungsten nitrate. Because it's a nitrate, I know it's going to completely break apart. The water separates the tungsten from the nitrate. The nitrate is just going to stick around. We're going to see that as a spectator in this lesson here. But it's going to have produced the tungsten ions that we have. All right? So that's how you read this table here. It gets a little bit more interesting as you start going downwards. One thing to be really careful of, let's say I gave you this compound here, CuCl2. Can you check whether this is solid or low soluble? Again, what you do is you first check the negative ion. The negative ion is chloride, so I'm now focusing in on this fifth row down here. Chloride with many things are actually soluble. They're going to be aqueous. Chloride with silver is solid. Chloride with lead 2 is solid. Chloride with copper 1 is solid. Well, wait a second. This is actually copper using its +2 charge. Copper +2 is actually, it's sort of sneakily here, it's actually in the all others case. So this charge here matters. Be really careful that copper 1 chloride would be low soluble, but copper 2 chloride is definitely soluble. So we'll just look out for that there. And especially as you start getting downwards, we start getting sort of combinations here. We start getting the basically everything with phosphates, carbonates. These ones here aren't soluble, with the exception of the ones that we said earlier. Alkalis, H+, and ammonium salts are always soluble. Right? So there's two ways of asking this question here. I'm going to introduce to you both ways, just one by one here. First way we started seeing a little bit last year is referred to as trying to write what's called net ionic equations. So let me just give you a sample equation here. Let's say I want you to take calcium nitrate, and I want you to react it with sodium phosphate, Na3PO4. Right? So this is back to grade 11. What we're interested in doing is we're interested in doing a prediction. Can you guess what the products are going to be? Can you balance it? Can you make sure all the atoms are accounted for? These ones here will always end up as double replacements, but that's the classification of the 6 simple types of reaction. This one here, they basically switch partners. Now, at first, we see both of these are ionic compounds. Both of these can be solid at room temperature because they form that lattice structure. It's a little bit hard to actually dissolve solid and solid. So what we usually do is we pre-dissolve this calcium nitrate. I add some water to it, and what I end up with is actually calcium nitrate, CaNO3,2, aqueous. I'm going to just pre-dissolve the Na3PO4 as well, just add some water to it. We always pretend our background is water. Na3PO4 also aqueous. We can verify that on the chart. Well, this one here is a nitrate salt, so you just memorize that nitrates with any positive ion, those ones are definitely soluble, aqueous, no problem. And this one here, sodium, is an alkali salt. It's a group 1 salt. Alkalis with any potential negative ion are also aqueous. For a properly worded question, the left-hand side should be both aqueous. The goal is to make sure that the ions are completely separate so that they can more easily mix together. So in a double replacement reaction, we don't need to check activity series. We still end up with the same products either way. We're going to have a compound here. Calcium is going to now be bonded with phosphate, and we're going to have sodium bonded with nitrate. A reminder again, in general, these numbers don't drag over. Just because there's a 3 there doesn't necessarily mean a 3. I do just need to check the charges myself again. Calcium is an alkaline earth metal. This is +2. Phosphate on the polyatomic chart here is -3. So therefore, my correct compound should actually be Ca3 with 2 phosphate ions. The NaNO3, Na is an alkali salt, NO3 is minus, so that's perfect. Well, no, the atoms don't match up. Remember, balancing comes as the very last step. Especially when you start having polyatomics. If they're the same polyatomic group, say I have PO4, at least I'm going to have 2 of them. I only have 1 PO4 grouping. Maybe I want to double it. I'm treating the PO4 as a unit, and I'm sort of saying double the whole thing. I'm not necessarily going, 2 phosphoruses, 2 times 4, 8 oxygens. I'm not actually looking in the little bits. 2 times 3 for sodium, that means I have 6 sodiums, so I need a 6 here. 6 sodiums means 6 nitrates. In this case here, nitrates come as 2s, so let's put a 3 here. Then I have 3 calcium, and voila, we have 3 calciums there. Right? Although for a properly worded question here, we should have the left-hand side definitely all aqueous. On the right-hand side, all bets are off. You can have a situation that both of these are aqueous. You can have one solid. You can have both solids. And the question will be different depending on what ends up happening. How do we check that? We can check our solubility chart. I don't really need to look up this one. Na and NO3, well, alkali salts are always soluble. Nitrate salts are always soluble. I know this one here will be aqueous. The only one I really need to check in this situation is the calcium phosphate. I want to know whether when these ions are in solution, do they mix well or do they form a low soluble salt that doesn't dissolve easily. So you go up to your trusty chart here. Notice that phosphates is way low on the table here. Phosphates with alkali salts like sodium are soluble. Where would calcium be? Well, calcium would be captured in all others. Calcium with phosphate would actually be low soluble. This one here is actually a solid. So now imagine with me this. I started off with 2 containers, right? This one fully dissolves calcium nitrate, fully dissolves sodium phosphate. Let's take a third container and let's just dump both of those liquids in there. what ends up happening is the NaNO3 remains aqueous. NaNO3 completely dissolves, no problem. But what's going to happen here is the calcium ions that were in the first solution end up realizing, wait, we're not very good at dissolving with phosphate. Currently, they haven't been mixed yet, but when they all get mixed in the same container, the calcium is going to start running into some phosphates, and this one here ends up forming a solid. This is a precipitate, PPT. This is a solid, crashes out of solution. So we started with sort of a dissolved bottle here, a dissolved bottle here. When you toss them in the same container, these guys realize, oh, we don't dissolve very well. Sure, a little bit might be left over to dissolve, but they're going to actually solidify out, and they're going to crash out as a solid here, calcium phosphate, Ca3PO42. Right? Again, it's totally possible that on the right-hand side, maybe both of them are precipitates, maybe both of them are aqueous. To help us analyze this a little bit, only for the purpose of this double replacement reaction, so far what we've done, this is referred to as a formula equation, because our equation is using all the chemical formulas, all the chemical symbols. What I'm going to ask you for in this section is I'm going to ask you, well, can you do it in a little bit more detail here? Can you actually write from the formula equation, can you write something called the complete ionic equation? We rehashed this a little bit during our introductory review, but here's where we see it again. A complete ionic, really simple. I want you to break up, dissociate any salts that are aqueous, but I want you to leave any solids alone. Right? Later on, we're going to even leave liquids alone, but we're not going to see any liquids out of this story. So let's keep the numbers here. Calcium nitrate is going to dissolve. It's going to dissociate. We're going to get calcium ions. We're going to get nitrate ions. Remember, the polyatomics stick around together. I still don't need to worry about the ratio. Because this was balanced to begin with, I just want to drag these numbers down. So 3 times calcium means I have 3 calcium ions. 3 times 2 for the nitrate means I have 6 nitrate ions. So really, this bottle that was labeled CaNO3.2 is a little bit misleading. It's not actually holding hands anymore. Because this is aqueous, it's been fully dissolved. We just have calcium ions and we just have nitrate ions just swimming around freely. Exactly the same here with the sodium phosphate. I have 2 times 3 means I have 6 sodium ions, 6 Na pluses, and I have 2 times the phosphate grouping, 2 PO4. Again, the label which says, oh, it's Na3PO4, it implies that we formed a compound. No, once you drop in water, the Na is swimming around freely from phosphate being stabilized by the water groupings. Now what we do is you potentially mix them together. As I mix them together, we have one solid that forms. That's our precipitate. I'm going to leave that alone, Ca3PO42. And then what I have is I have one more salt here, NaNO3. It looks like when I switch partners, I end up forming a new bond. I end up creating a new compound, sodium bonded with nitrate. But this one here being aqueous, just like before, water would have separated the positive from the negative. So I just have 6 sodium ions and 6 nitrate ions. If anything, this is a very tedious equation, because not only do I need to check all the numbers through, I can't do this shorthand. Well, it's kind of like they're holding hands, but aqueous means they're not. So that's the complete ionic equations. The only thing that I didn't dissociate here is any solids that I have. Potentially, if I had a reaction that produced 2 solids, you keep both solids together. Now what you're going to do here is, depending on your complete ionic, we can write something called the Net Ionic Equation. And Net Ionic Equation, you only do this for this double replacement style reaction here. The Net Ionic Equation, I want you to cancel out any spectator ions. Like spectators at a game, they basically watch the game, they don't actually participate in the reaction. So even though your double replacement looks like, oh, we're always starting with calcium nitrate, sort of 2 combinations, and we end up with 2 combinations here, we end up realizing, wait a second, I actually have 6 Na plus, that was before, totally broken up. I still have 6 Na plus over here, those are spectators. Before and after, they didn't change, just cancel them out. Same thing with the nitrate here. I have 6 nitrates. I have another 6 nitrates over here. Those ones there end up canceling out. They are identical before and after. The nitrates used to be swimming around this bottle. The sodium used to be swimming around this bottle. Even as you toss them together, it's a little bit misleading writing them as NaNO3. They're actually not bonded, or they're not holding hands. The nitrate ions and the sodium ions are swimming around just like they were before. They didn't participate in the reaction. So therefore, in overall, what's actually happened? Well, what's actually happened is, for every 3 calcium ions in my first bottle, as they run into 2 phosphate ions, these ones here initially were in 2 separate containers, so they couldn't react. Once I pour these together, the calcium runs into phosphate, and this one here actually does solidify. This one here is low soluble. This one here does actually bond together. So calcium does form a attachment with phosphate, right? And that's referred to as a net ionic equation. Again, for simplicity, a properly worded question should have the left-hand side all aqueous. The right-hand side should be, well, it could be anything. It could be both aqueous. In this case, it's one precipitate. It could even be two precipitates here, right? So let me just pull out one more question for you to practice here. Okay, so let's try this one here. I want you to, for this example, I want you to write the formula, the complete ionic, and the net ionic equations. Net ionic. For the following mixture here, I'm going to give you these salts here. Let's take strontium hydroxide. Let's react with magnesium sulfate. And then you're going to predict the products. Okay. Again, I'm going to ask you just pause the video, try it out for yourself. Use the solubility chart. Right. When you come back, you can check your work here. Let's have a look here. Well, I predict this is going to be double replacement, so they're going to switch partners. I'm going to end up with strontium and sulfate, and I'm going to have magnesium with hydroxide. Make sure you've written the correct compounds. So strontium is alkaline earth metal, +2. Sulfate is -2. Everything is good. Everything is even balanced, so even nicer. This is so far the formula equation. I just have the chemical formulas for all of these here. But I want to know, based on our solubility chart, maybe I've labeled the bottle as SrOH2, but maybe it's completely soluble and water has actually broken it apart. So let's just check our solubility chart here. This time there's no alkali salts or sodium salts. I need to check everything one by one. Let's check hydroxide here. Is it okay with strontium? Is it okay with magnesium? Right? So go back up to your table here. Hydroxide is right here. Hydroxide with strontium is low soluble. That can be aqueous. Hydroxide with magnesium, magnesium would actually be all others. With magnesium is actually low soluble. That's actually going to be solid. So again, that's consistent so far. For a properly worded question, the whole reason was to have an aqueous salt, mix these up so they can actually dissolve easier. They can actually combine easier. With magnesium, they're not good. What about for sulfate? Is sulfate good with magnesium or is sulfate good with strontium? So let's look up here for sulfate. Sulfate and strontium is going to be low soluble. That's going to be solid. But sulfate with magnesium is actually going to be soluble. So in that case there, we're going to have, again, properly worded question. We should have aqueous on the left-hand side. Strontium is not okay with sulfate. That one there is going to be a solid. Oh, this time here, actually, both of them were solid. That's fine, right? Like I said, there's no bets on the other side. That's the formula equation. This is so far written everything just in the chemical formulas. The complete ionic equation takes all the aqueous ones and dissociates them. So for example, strontium, Sr +2, I have 2 hydroxide, Mg ions, I have sulfate ions. Remember the implication there is even though your bottle is labeled strontium hydroxide and magnesium sulfate, because we've identified them as aqueous, they're actually not holding hands anymore. It's actually just strontium ions, just hydroxide swimming around, or just magnesium and just sulfate swimming around. Now all we do is we put them all into one and the same container together. Now all 4 ions are now together. There's strontium ions, there's hydroxide ions, magnesium ions, sulfate ions. So far, I've only been doing sort of, strontium was only trying to make sure it's dissolved in hydroxide. Now strontium potentially has another ion it may not be good dissolving with. And lo and behold here, strontium sulfate here is actually low soluble. Even though we initially had the ions in the individual bottles, when you put them in the same container, these two say, wait a second, we don't dissolve very well, and they're going to form out a strontium sulfate solid. Similarly with the magnesium hydroxide, magnesium was fine dissolving with sulfate, but magnesium and hydroxide also forms a low soluble. This one here is a second precipitate. Magnesium actually forms a new bond with hydroxide, and this ends up forming magnesium hydroxide. So the complete ionic equation is actually, okay, so take these equations as is. Strontium ions, 2 hydroxide, magnesium ions. Because the other ones were low soluble, we just keep them as solid. I actually formed 2 precipitates here, strontium sulfate, and we actually form MgOH2. Those have actually solidified out. Now, to be sure, even for low soluble things here, there will be a few remnant ions still in solution. But the more important thing is usually the ion concentrations are high enough, and basically the precipitates have formed. So in this question here, the complete ionic here, we've actually formed 2 precipitates. a precipitate, a PPT of strontium sulfate, and a precipitate of magnesium hydroxide. What about the net ionic equation? Net ionic equation is the overall equation. We just cancel out any spectators. We cancel out anyone that stays the same. We look at this and say, wait a second, nothing stays the same. We were strontium ions before, and now we're solidified. We were magnesium before, and now we're solidified. So in this question here, our net ionic is it's the very same complete ionic equation. There was nothing to cancel out, so be it. Right? So very, very tedious, but that's actually telling you in this double replacement reaction, we physically do end up making two new compounds. At first, the ions were just swimming around, and later on, we end up forming two solid materials. Right? So this is one way they can ask this sort of solubility style question here. There is one other setup. This is more of an experimental setup, again referring to your solubility chart. And this is a method known as selective precipitation. Maybe we can take advantage of this, which ones are low soluble, which ones actually form solids, to actually separate mixtures. So let me just give you the overall goal here. We're going to use a precipitation method, use precipitation to separate ions from solution. Right? Because when they're ions and they're fully dissolved, they're all mixed up, right? They're all together. But what we're going to do is we're going to be adding random salts here. And as I add those random salts, if it's a solid and it ends up crystallizing out, I can end up separating that from solution. Selective precipitation. Okay. So let's just do this by way of an example here. Let's say I have a beaker. This beaker here, in your sort of practice questions here, it may say, like, it may contain silver ions, it may contain barium ions, it may contain nickel ions, right? So I have a mixture that potentially has these three chemicals here. You notice that they are ions, so that means they're fully dissolved. Water has stabilized these ions here. Our goal is to separate off these ions one by one. And what we're going to do, there's actually multiple answers for this, but how you're going to do this here is you're going to check the solubility chart. Check the solubility chart and add, in this case here, these are positive ions, so we're going to add a negative ion. Add anions that only precipitate one cation at a time. Eventually, I'm going to separate all three. But what I want to do here is I want to start separating the easier ones to pull off first, then the next one, then the next one, right? And it really does matter which one you start with. Sometimes you have multiple options here. Let's just keep in mind we have silver, we have barium, we have nickel. Let's just go back up to the top here. Silver, barium, and nickel. In this case here, we're not going to do the really soluble ones up at the top. I'm going to look at some of these ones, these combinations here that are actually low soluble. So remember, our choices so far in this question, we have silver ions, we have barium ions, we have nickel ions. I want to choose a salt, choose a negative ion that will solidify one of these and not all of them. What's the problem if I pull off all of them? So just erase this here. Let's pretend I throw in some phosphate, okay? Well, is phosphate good with silver? Well, no. Phosphate and silver will be low soluble. How about barium? Barium and phosphate will be low soluble here. If you toss in phosphate, you're going to end up, all three of them are going to crystallize out. You're going to get all three powders all at once. They would not be separated. So our job here, again, is I want to add in something that only precipitates one of them. So can you find one of those choices here? There's multiple answers. I would look at maybe a little bit higher here, and I would say, well, taking a look here at the top, if I add in a chloride or a bromide or an iodide, this one here with silver is low soluble. But what about chloride with barium? Well, barium's not silver, it's not lead, not copper here. Barium's actually up here, so that's going to actually be soluble, no problem. Nickel is no problem swimming around with these ones. So in this case here, silver is very easy to pull out a solution here. I'm going to add, let's say, chloride for argument's sake. Again, although chloride is the ion that we want, I want to solidify this out as AgCl. You're never going to have a bottle of pure chloride. Your bottle will always have a counterbalancing positive ion. Just to guarantee that I have a soluble salt that can release the chloride, I'm probably going to choose maybe an alkali compound with a chloride. So again, there's many different ways of doing this here. One solution I'm proposing here. Let's add NaCl. And again, you'll say, whoa, where did that Na come from? Well, this is an alkali salt. Alkali salt's guaranteed to break up. As you add NaCl, sure, there's going to be leftover spectator Na+. I don't really care about it. What I care is the NaCl bottle has tossed in extra chloride, which I've just figured out, chloride and silver, they don't dissolve very well together. They're going to actually solidify out to become AgCl. So add NaCl to precipitate, to PPT, AgCl. Cl is perfectly fine swimming around with barium, swimming around with nickel. And then what we're going to do here, there's sort of an intermediate phase here. So if there was silver in solution here, the silver chloride is going to precipitate out. It's just a one solid, and now I've managed to separate silver from the other two positive ions. You will need to sort of in between here, it's sort of implied. We need to do a sort of filter, stick it through a filter paper. We might use this terminology of decanting. Basically, you're pouring the solution very carefully so that the solid sticks around the filter paper. And now upon filtering it, now I have a bottle, I'm hoping, that has just barium ions and just nickel ions left over. All right? So now it becomes a little bit easier. Now I don't need to worry about the silver. I'm looking at nickel, I'm looking at barium. I'm looking to add a negative ion that only precipitates one of these, but not both of them. So barium and nickel. Let's go back to the top here. So I notice here, let's try sulfate. How about, right? If I try sulfate, sulfate is low soluble with barium. Barium sulfate here will solidify out very, very quickly. But where would nickel be? Nickel is not in that bottom case here. That means nickel here has to be on the top. Nickel with sulfate is perfectly soluble. So nickel is perfectly happy swimming around a solution with sulfate, but barium is not. So I'm going to add a compound that has sulfate inside. Again, you're not going to have a bottle of just pure sulfate. Well, let's just throw in sodium sulfate. Again, the sodium is a spectator. I could care less about it. Let's add sodium sulfate. Again, this is not the only solution. Add sodium sulfate. You're going to get 2 sodium ions and the sulfate. What I really care about is I just care about having this negative ion. And in that case there, that sulfate is good to precipitate out barium sulfate. It's going to separate the barium ion from the nickel ion. Sure, it's going to have complex the barium with the sulfate. We now need to separate the barium from the sulfate, but that's done later on. So if you add sulfate here and you end up seeing a solid end up forming, I'm guaranteed that that precipitate is actually barium sulfate. Again, there's this filter and decanting step that's sort of implied. I would basically dump this through a filter paper, I trap the solid off, and now I just have a beaker that potentially just has nickel, and now I just add something. This time it's not separating, this time it's just removing the nickel from solution. So I'm going to add something that nickel is not good at dissolving. Now we can really use the bottom of the table. Earlier we couldn't use phosphate because it was low soluble with everything. But now that I've assumed the silver and the barium are gone, now I can use any of these. Let's choose carbonate. If I use carbonate, aside from the alkali salts, H+ salts, these ones here that are always soluble, carbonates prove pretty much everything. They don't dissolve very well. So including nickel. So let's add in a carbonate. You're not going to get a bottle of just pure CO3 2-. So what I'm going to do here is I'm going to add, let's say, sodium carbonate. Well, where'd that sodium come from? Doesn't matter. The sodium there is just a spectator. The sodium is just going to sit in solution, not doing anything. But more importantly for us is, oh, we actually got the carbonate that we need. We're going to be able to precipitate to PPT the nickel carbonate. And that's how we've done selective precipitation. By adding salts one by one, by pulling out the ions one by one as a solid, I managed to separate the solution. Even if the question is worded, the solution may contain silver and barium nickel here. If you add one of this and no solid forms, maybe that's just an implication that there was no solid. You can then keep going, right? Again, there's an implication that once you form a solid, you do need to filter it off before the next step, but you're choosing to pull out one precipitate at a time. So I'll leave it off there. You can practice through some questions and let me know if you have any problems. Thanks, guys.